So these are added notes. So what I would suggest is when we're done with them, actually taping them inside of your book. I'll show you what that could look like. So right before section 5.4, I taped it in my book. I folded it, and then I taped it so that it could be folded out like that, so it doesn't affect any of your notes in here. But then when you find it later, it's always in the same place. So you can do that afterwards. So permutations, that's part of a branch of mathematics called combinatorics. It's just a fancy word for counting. Some of this is going to be review. So we've already done questions like this. A new car is being built. You have 3 choices of color, 2 choices of transmission, and 2 interiors. How many cars could be built? Well, you have 3 decisions to make. Every time you need to make a decision, draw a space. Underneath those spaces, color, transmission, interior. On the exam, they'll expect a little tiny explanation. It can be as simple as that. The marker will be, oh, they meant color, transmission, interior. How many choices of color? 3. How many choices? 2. How many choices? 2. 3 times 2 times 2, 12 ways. So this is the fundamental counting principle where you can draw spaces to figure something out. And we've done questions like this already. So here's another one. Using the numbers 1 to 7, how many 3-digit numbers can be made if you're not allowed to repeat and you are allowed to repeat? So again, it's a 3-digit number. You would have 3 decisions to make. What's my first digit? What's my second digit? What's my third digit? If you were not allowed to repeat, does it make sense that you could choose any one of the 7 numbers? Okay? First thing that sometimes students get mixed up on is if I put in a 7 there, like, oh, you chose the number 7. No. I had 7 choices. I could have picked any one of those 7. So, for example, I picked the 5. You don't know if you picked the 5. You could have picked any of the 7. But if I chose the 5, now how many choices do I have for my second number? 6. And then 5. Okay? I think this makes the most sense to do with spaces. This is also equal to 7p3. When you have this notation, 7 pick 3 or 7 permutation 3, there's 3 spaces starting with the number 7 going down each one. If you are allowed to repeat, you have 7 choices, 7 choices, 7 choices. So this would be 343. This one here would be 210. Now in example 3, I want you to add this in because I want to connect it to that first question. We're only going to use the numbers 1 to 7. And this is something that's a little bit new. They've done this a bit in your textbook, but this question has a restriction. It says how many 3-digit numbers are even, we're not allowed to repeat. Now the strategy is to deal with the restriction first. So this is what the strategy looks like. Still have 3 decisions to make, but I have a restriction that this last digit has to be even. So underneath it, because there's a restriction, I'll just write a little explanation. Using the numbers 1 to 7, probably even easier if I write them out. How many are even? The 2, the 4, and the 6. So I would have 3 choices for my last digit. Now I don't know which number I picked. I could have either picked the 2, the 4, or the 6. So let's say you pick the 2. Now for your first digit, there's no restrictions on it, but how many choices are left? Now there's only 6 numbers that are left that could go there. And then 5 after that. 30 times 3 gives us 90 ways. Now what happens if you didn't deal with the restriction first? This is what it would look like. You're like, okay, I need it to be even. I can have any number first. That's true. So I have 7 choices. Then I could have any number second. That's left. That's true. Then I have 6 choices. Then I want to put an even number here, but I don't know what number to write. And the reason I don't know what number to write, let's go here, take this away. In my first one, I could pick any of the 7. I could have picked a 1, right? In my second one, I could pick any of the 6 that are left. I could have picked a 3. If I pick the 1 and the 3, how many even numbers are left? There's 3 left. So I think, oh, I should put a 3 there. But in picking my first numbers, I could have picked a 2 at the beginning, right? And if I picked a 2 at the beginning, when I got to here, I'm like, oh, I should only write a 2, because I only have 2 even numbers left. But I could have also picked a 2 and then a 4. And then if I tried to do this last, I'd have to put a 1. So the problem with dealing with your restriction last is you don't know what number you could put in there, because it could have been a 2. Those numbers could have been used up. But if you deal with the restriction first, say, first of all, I'm going to put a 2, a 4, or 6 here as my last number. That guarantees that it's going to be even. Now how many choices do I have left? Only 6, only 5. So if you have a restriction, you have to deal with the restriction first, because this won't work. You won't be able to put a number in there. So I'd like you to try this one. Again, numbers 1 to 7. How many are odd? So again, we're dealing with a restriction. And once you get your answer, I want you to see if you can figure out another way to solve this same question using the results from questions 2 and 3. Okay, first of all, most people probably did it this way first, right? 4 choices for odd numbers, 1, 3, 5, and 7. And then 6 numbers are left, then 5 numbers are left to get 120. But I also said once you get your answer, see if you can see how you could use the answer from question 2 and question 3 to figure this out. What did question 2 find? All the numbers. Right? If we go back to question 2, can you see that without repetition, we found that there was 210 numbers in total. That was all the numbers using 1 to 7. What did we find in question 3? We found of those 210, 90 are even. So if you knew that there was 210 numbers in total and 90 of them were even, how could you use that information to find out how many were odd? Yeah, we would just need to subtract, okay? So another strategy, and I have a name for this strategy. I call it the not strategy, because you count something that's the opposite and subtract it from, this is how I describe my not strategy. Take all of them and subtract the bad ones. Put bad in quotation. In this case, all of them, there was 210. Subtract the bad ones, 90. Why are the bad ones bad? because they're the even ones. And what are you left with? 120 odd ones. Now, in this example, I would only say use the not strategy because you knew the answers from question 2 and question 3. Normally, the regular strategy would be just as fast. But there's going to be some questions that we do that it's going to be much easier and much faster to count the bad ones and all of them and subtract than it will be to try to count it directly. So we've already been introduced to sort of 2 new ideas in this class. The restriction, dealing with the restriction first, and now the not strategy. So those are new ideas. The spaces, you've already learned that. Okay? How many 3-digit numbers can be created using the numbers 0 to 9 without repetition? So again, try this first on your own. Okay. First of all, when you did this on your own, did you realize that there was a restriction? Okay? The restriction is the fact that, is this a 3-digit number? What number is that? 93? Does 93 have 3 digits? No, 93 has 2 digits. So if you wanted a 3-digit number, there is a restriction on that first digit. You can't start with a 0. So how many choices? You have to deal with your restriction first. How many choices do you have for that first digit? Everything but 0, 9 numbers. And if you wrote out 0 to 9 and you picked some number out of there, how many choices do you have for your second one? 9 again. Why? Because now 0 gets put back in. But one of the numbers is gone. And now 2 numbers are gone. How many choices do we have for the last one? 8. 81 times 8 gives you 648 in total. So I think that one a little bit harder to see that restriction, that you can't start with a 0. Okay, moving on. Stuff you've already seen. Factorial notation. Evaluate without a calculator. Or in case C, they wouldn't say evaluate, but they would say simplify. So when you are evaluating factorials, in order to simplify the expression, you always find the biggest factorial. 7, obviously the biggest one in the first one, and start expanding until you get to the number that's on the opposite side. I mean, 7 factorial would go all the way down to 1, but as soon as I get to 5, I'm like, I'm just going to stop at 5 because I have a 5 factorial on the bottom. Those would cancel out. Just left with 7 times 6. And you can do that without a calculator. Okay? Much better than going 7 factorial is 5,040 divided by 120. That must be 42. Yeah. Not a good choice. Second one, what's the biggest one? 10. I go 10, 9, 8, 7. Get to 6. I'm going to stop there because I have a 6 factorial on the bottom. Those are going to cancel out. I also have a 4 factorial on the bottom, so I'm going to go 4 times 3 times 2 times 1. If this was without a calculator, can you see that 4 times 2 is 8? So those would simplify. And I'm switching colors because if you just look at this directly in your notes, you're going to be like, what did I all do? Well, the 6 factorials, that makes sense. 4 times 2, that canceled out with 8. The 9 and the 3 I'm going to cancel out because that would simplify to leave me with a 3 and a 1. So now that what's left? It's kind of messy. On the top, I have 10 times 3 times 7. On the bottom, everything canceled out, so it's just 1. So that would leave me with 3 times 7 is 21 times 10, 210. Now, when we get to algebraic expressions and we want to simplify, so evaluate actually doesn't work with C, but you could have the thing that would say simplify. Simplify would mean to get rid of your factorial signs. Just like you do with numbers, you have to decide where is the bigger number. Here was 7 and 5. I hope it was pretty easy to see that 7 was bigger than 5. But once you get to algebra, it's not always as easy. In this case, it's not too bad. Which is bigger, n or n plus 2? N plus 2. So if I start expanding, I would write n plus 2 multiplied by, and then when we expand, we always write 1 less. What's 1 less than n plus 2? N plus 1. What's 1 less than n plus 1? N. And once we get to n, we're like, oh, that's what's on the bottom. And those will simplify. So we're left with our simplified expression as just n plus 2 times n plus 1. Yeah. If you're going to highlight something here, this comes up later. We've only done permutations so far, but a permutation is counting of objects where the order matters. And we're going to find out later in combinations, combinations is something where the order doesn't matter. Okay? I'll give 2 different examples. If you run a race, someone's going to get first, second, and third. They're going to give a gold medal, silver medal, and a bronze medal. Does it matter the order? Yes, right? If it's the Olympics, they're not like, oh, good job, this time we're going to play the third person's anthem. Is everybody okay with that? Right? And we'll give them the silver medal. No, here's like, no, I won gold, you have to play my anthem. I get all the $1 million worth of endorsements. I'm glad you finished third, you get the little medal, and nobody ever hires you for a commercial. So the order matters. But if there was something else where I've got 3 prizes, the prizes are all the same. If you got to pick first or second or third, if you were one of the 3 that wins the prize, it wouldn't matter what order. You're going to get the same thing. So sometimes order matters. That's a permutation. Sometimes order doesn't matter. That is a combination. And we're going to learn about that later. So for this, write all the permutations of A, B, C. Well, you could have A, B, C. You could have A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Of course, that's writing them all out. To make sure that we know how many we were supposed to have, we can use spaces. How many choices for the first letter? Any of the 3 could go first. But once you've used up one of those letters, then 2, then 1, this is equal to 3 factorial, which is equal to 6. So our sample space should have 6, and we do. So you've already learned the permutation formula. That's on your formula sheet. NPR. We've also noticed that this is related to our spaces question. The R is the number of spaces. And that N is the number you would put in the first space and go down each time. Okay? If you have N numbers and N spaces, here's the formula that shows that you should get N factorial. But if you thought about, 5p5, if you think about 5 spaces, starting with 5 and going down by 1, it should make sense that that's 5 factorial as well. Find the number of ways a program where the order matters of 4 pieces of music can be made from the Sturgeon Heights Collegiate Wind Ensemble's repertoire of 10 pieces? Well, if the order matters, you could do this as a permutation, 10p4. You could do this as, I have 4 decisions to make. What's going to be my first piece of music? How many choices do I have? 10. Then I have 9, then 8, then 7. It would be a terrible concert if they allowed repetition. Today we're going to play 20 songs. We're really good at O Canada. We're going to do that 20 times. And if you stand and applaud at the end, we might come back for an encore. Oh, that would be, I just went. Yeah, wait for it. All right. So I won't put, I mean, you could multiply this out with your calculator. The answer doesn't really matter. Number of permutations of the word math, the order matters. Well, you could do spaces 4, 3, 2, 1, which would be 4 factorial. So if the letters are all different, it's really easy, because you have 4 letters, it's just going to be 4 factorial. Probably don't even need the spaces. But this will lead into, and I'll do this question first, and then we'll get into the one that it leads into. 5 people come for math help, and there are 12 desks. How many ways can the students be seated? The order matters. Now, this is the first time that a permutations question and your thinking clash with each other a little bit. Okay? This is a spaces question. The number one thing that causes people problems on this is that you have to decide how many spaces you're going to put, and then you can put numbers into those spaces. And students want to write 12 spaces because there's 12 desks. And you normally put students into desks. So your physical thought of the question causes you to make a mistake. Because the spaces are there for decisions. If 5 people come for math help, how many decisions need to be made? Only 5. Right? Person 1 walks in. How many choices do they have? They have 12. Because they could sit in any of the desks. Okay? Person 2 comes in. They see one person seated in the desk. Okay? This has never happened. Right? I can't put another 12 in there because it's never happened that a student goes, oh, there's 12 desks, even though someone's sitting there. I'm going to go sit on their lap. That becomes a very awkward math help that day as a result. No, they only see that there's 11 desks left that are open. They sit in another one. Yeah, you're shaking to think what it would happen with. Oh, 10, and then 9, and then 8. This could be represented as 12p5. So one of the places that we like to use the permutations notation is if the number gets really, really big. Like if I asked, how many different seating plans could we have in here? Well, I've got 5, 10, 15, 20, 25, 31 desks. Right now in our class, we have 25 people. So with 31 desks, 25 people could walk in, 25 decisions could be made. I could draw 25 spaces. But this is where it's much nicer to go, I'm going to start with the number 31. There would be 25 spaces, 31p25. Now, this is the other crazy thing about permutations. Okay, 31. Do you know where the permutations button is on your calculator? You hit math, you go over to probability, NPR. So if you wrote 31 first, it'll automatically get put in. 31p25. Wow. 1.14. See that e to the 31 at the end? 1.142 times 10 to the 31. That's how big that number is. So some years, I say, I'm going to put up a random seating plan, and if you guess the random seating plan correctly, then I give you, you don't have to come for the rest of the year, don't have to write the final exam, I'll just make your mark 100%. Okay? Some classes, we had time, they actually said, let's try, let's guess. So they start, they guess, they go through, and like, what are your chances? 1 in whatever nasty huge number that is, times 10 to the 31. You would, I guess technically you would say that that is about 1.1, this is the proper word, 1.1 nonillion. I know it's one of my dreams to become a nonillionaire, but I don't think it's going to happen. Huge number. Then, oh, I was so bad. You know what I did one year? I had a student, I had the seating plan up on my screen so you couldn't see it. Obviously not on here, it'd be a lot easier to guess. And I had a student, and they were all trying for this 100%. And they said the first time, like, yes. They said the next one, yes. I lied the whole way until they got to like 2 left. And then I started laughing because they thought, oh, I'm so close to getting the seating plan. That was mean, wasn't it? Just a little bit. Okay. All right. Now I'm going to get you to stroke this out. And we're going to use, I think what the textbook had is better descriptor. So we've done these before already as well. Permutations with identical objects. These are the ones like Samantha with the 3 A's. How many permutations are there of the word egg? I'm not going to explain the reasoning before, but we know that our strategy is, well, egg, if it was 3 different letters, it would be 3 factorial. But because we have identical objects, we have to divide by 2 factorial. In Assisipi, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factorial. But we have the S's repeated 3 times, so a little explanation. Just an arrow and an S is wonderful explanation for math in this situation. We have 2 I's and 2 P's. Anything else repeated? We only have the 1 E and the 1 A, so you don't need to add anything else, and simplify it from there. Now, if you're typing this into your calculator, you may need to put an extra set of brackets around it. Anytime you have more than one thing, either in your numerator or denominator, it's not a bad idea to add those extra brackets. So, identical objects. We've seen questions like this before. We've seen it in some different situations in our notes. So we'll look at some other things that could be identical object questions. Here's one. A contractor sold model homes of type A, B, and C on a street. 3 of model A, 4 of model B, and 2 of model C's. How many ways can the houses be arranged? And this is where, if you get this question out of context, would you be able to recognize that it was an identical objects question? Because that's going to be the hardest thing in this unit. How do I know that something's an identical object question, not just a spaces question, not a spaces with restriction question? Okay, so you have to read through this and say, what do I have? I have 3 of model A. I can represent that with 3 A's, 4 of model B, 4 B's, and 2 of model C. Probably one of the, if you went with the spaces first and did, in this case, there are 9 houses. If you did 9 spaces, when you went to put your number into that first space, how many choices do you have? You only have 3 choices, either A, B, or C, and you feel like something's not right here. Why? Because I have identical objects. Once you recognize it as an identical objects question, the question becomes relatively easy. And we've done one like this before. Okay, John lives 3 blocks north and 6 blocks east of school. So this is where John lives, and this is school. And we have done questions like this before. Do you remember the 2 strategies we looked at? We looked at, well, if you went this way, that would be represented by 3 norths and then six easts. That's for any Monty Python fans out there. Of course, then it is the identical objects. You have 9 factorial over 3 factorial, 6 factorial, whatever that number is. And the other strategy that we looked at was counting. You could go 1 here, 1 here, 1 here, 1, 1, 1, 1, 1, 1. All those straight paths, the only way you could get to those points would be 1s. But then this one becomes 2. And if I have 1 way here and 2 ways here, this will be 3 and 3. 1 and 3, this will be 4. 3 and 3, this will be 6. 3 and 1, 4. 1 and 4, 5. 10, 10, 20, 15, 6, 7, 21, 35, 56, 28, and this should equal 84. So we could do this question with counting the spaces. Now, if it was a regular rectangle like this, just the repetitive things, I think, makes the most sense. Although sometimes I've seen these questions with a new piece of information, okay? We're going to say that Cynthia lives there. And now, every time John walks home from school, he has to walk past Cynthia's house. I know, a little bit of a stalker, eh? So now how many ways can he walk home if he had to walk past Cynthia's house? Oh, and then I'll add another part. So I think for this one, can you see now that if he had to walk past Cynthia's house, that he no longer ever goes to this area or to that area, right? He'll never walk on those roads again because otherwise he'd have to backtrack to get to Cynthia's house. So now considering that, well, there's one path there, 1, 1, and 1. He could get here in 2 ways. 1 plus 2, 3 ways. There would be 4 paths that would get him to Cynthia's house. And after loitering there for a couple of hours, now he heads home. There would be, since there's 4 ways here, does it make sense that there'd be 4 ways here, 4 ways here, 4 ways here? No new paths. Same thing here, 4 and 4. 4 plus 4, this would be 8, this would be 12, this would be 12, 24, 16. Now there would be 40 paths home. So if he had to walk past Cynthia's house, now there's 40 paths home. So this is an example of where the spaces, or counting it along the grid, probably is easier. Now if in part C I say 2 months later, something happens that he can walk home, but he's not allowed to walk past Cynthia's house. How many ways could he walk home now? This would be an example of the not strategy. You know that there's 40 paths that go through Cynthia's house. There's 84 paths in total. How many paths don't go through Cynthia's house? 84 minus 40, 44 paths left. I shouldn't be allowed to make up stories. Okay, we are going to stop here for now.